talking about how to make leap to quantum PCPs.
Okay. So hello, good morning. So this talk, I started off with the comic, and then made the title, and then made the talk. So, so I'm not going to claim today to prove anything. I just want to give some intuitions as to how last year Anurag, Anshu, Nico Breuckmann, who are at Harvard and Bristol respectively, and how we proved the NLTS conjecture, and maybe how one should move forward towards a proof of quantum PCPs. So my goals are very simple. I want to give a small recap of how to think about NLTS. It's very light. It's not based on codes, really. It's just some very simple pictures. And then say what I think are next steps. Okay. So to preface, I mean, if you're unfamiliar with the quantum PCP conjecture, the setup is quite simple. We're interested in Hamiltonians defined by local interactions. And in particular, we'll be interested in Hamiltonians whose local interactions don't specifically fit on a lattice, but the first thing we always think about is Hamiltonians that fit on a lattice. And the Hamiltonians are very simple. They're, say, like k local interactions, and the k local interactions are described by 2 to the k size matrices. And for any Hamiltonian, you can think of it as an interaction on all the particles, just by the tensor product structure. And then the whole Hamiltonian is just the sum of these interactions, and we want to understand properties of this large matrix. So it's a large matrix, but there's not that many of them because they have this succinct description, because you can describe each of the local terms HF, right? So they're a special class of large matrices. And what we're really interested in is just figuring out what the low energy states look like. And energy just means eigenvalue. So we just want to understand some simple properties of what the low energy set of states for this Hamiltonian are, and even maybe what that energy is. So the famous result is that it is QMA hard to calculate this value up to some inverse polynomial precision. You can make this like n squared, or I think, or n cubed, based on exactly how you do the reduction, where n is the number of particles. Okay, so you might say, okay, well, it's hard to do this. Then what do you do next? Well, you say, okay, how hard is it to approximate? And there's sort of 2 regimes. So we know that the minimum eigenvalue, maybe it sits here. Getting anything below a small polynomial above that is going to be QMA hard. And then somewhere up here at some constant past the epsilon times n past the minimum eigenvalue, it's NP hard to find that. And the rationale for this is that the classical PCP theorem proves hardness for classical Hamiltonians, and that's a natural subclass. So we know that approximation is NP hard to some epsilon. And what the quantum PCP conjecture says, it's hard to get past some other epsilon. Maybe they're not exactly the same, but there is some other constant epsilon prime for which finding a ground state below that energy is going to be QMA hard. Okay, so how would you go about proving this? Well, you could try to do the classical PCP route. You might say where you follow every step one after another, but the big issue that comes in the way is that there's the no cloning theorem. So if you think about Denur's 2007 proof of the PCP theorem, it really came down to 3 steps. One was this notion of pre-processing, where she took the constraint problem. Here you could think of it having an interaction graph, like 3 coloring, and she made sure that it was expanding. And then whenever there was a variable that occurred with high in many of the clauses, she instead took that one variable and replaced it with a cloud of variables. And then she connected those cloud by just consistency checks, making sure they have the same value. Then there's this step of gap amplification, where instead of each vertex in the constraint describing itself, it sort of describes its neighborhood. It says not only what color it is assigned, but what color each of its neighbors is assigned, what color 2 doors down, etc. And you have it describe its constant size neighborhood. And now the consistency check is a little bit easier to do, because now you can check that whenever 2 vertices describe the same point, as in, so there's a point that's in their the intersection of their neighborhoods, you can check consistency between that. And this step actually shows that this problem has a higher unsatisfiability, so it's amplifying the gap. Okay, but now each vertex is describing this neighborhood, and that's a little problematic because the alphabet has grown really big. The variables are acting on the coloring. It's like this tensor product. So she does this. She applies error correction to reduce the alphabet, and again, there's this component where she has to replace high locality variables with this cloud. And then you repeat this log many times, and you get the amplification for the classical PCP theorem. Okay, but the problem is that many of these steps violate the no cloning theorem, although some of them can be avoided. Principally these ones in red all violate the no cloning theorem. In fact, I'll say that this other step of applying error correction to reduce the alphabet is also not trivial, but somehow there's going to be this inherent tension between no cloning and trying to do this PCP amplification. So maybe this was too hard. Let's step back. So let's see if there's another way to tackle this, or maybe even to refute this problem. And to do that, we have to say one thing about state complexity. So Tony had a great talk earlier describing state complexity, where morally it was this very simple idea that there's this decision complexity class of, it could be saying something like, does C accept any quantum state? And there's an analog state complexity class, which is now instead asking to build the quantum state itself. So both of these situations, you can ask about an object C. In one case, you want the binary answer. In the other case, you want the state, which matches said description. Okay, so how does the state complexity paradigm connect to the quantum PCP picture? Well, to do that, let's define a notion of state NP. I don't know if this is the right notion, but something I define, which you could just think of it as a set of classical representations of quantum states. So the idea is, what do you need out of this classical representation? It's given the representation xn, it's supposed to morally represent some state psi n. And the requirement is you want to be able to calculate the trace of O psi n for any local observable O just from the classical representation. There should be a polynomial time algorithm, classical, that lets you calculate that expectation.
What's a local observable? One that acts on constantly many qubits?
Yes. Okay, yeah. So local observable, anything that acts on constant many qubits. So here's some simple examples of things that could be in state NP. One could be like the description of a constant depth circuit. If you have a constant depth circuit, you can always calculate this on a classical computer because you only have to check a limited constant size light cone. Other things that might be useful is like the description of a matrix product state. Once you have a matrix product state, you can, close the tensor. Or another option that's sort of a little bit more esoteric maybe is to list all the stabilizers for some stabilizer state. If you list all the stabilizers, you can actually calculate this for any local observable. Okay, here's some examples which aren't. So the simplest would be just a list claiming to describe a map. Something that says, okay, when you tell me the oracle O, here's what the value is. Or, and this is because it's hard to check, right, whether all those local observables actually correspond to some state. So if there was a state underlying it, you might have just come up with answers that were correct locally, but they don't. There's nothing consistent. The second one that's probably a little bit more relevant that a lot of you have thought about is the notion of like a classical shadow. It's hard to check if a classical shadow actually corresponds to a state. So, okay. So how does this connect to the quantum PCP conjecture?
So basically, you want that as a way to check that the observables you compute from that actually.
Right, exactly. So you want to be able to check that there's a bona fide state. So in the case of, for example, when we have the constant depth circuit, well, you have a circuit that generates the state, so the state is well defined, right? You don't need to know what the state is. You don't need to be able to write it down, but just you need to know the existence of one. Yeah, so that would be another reasonable example. So if you give anything where you can calculate the traces with respect to local observables, and you prove that it is a state, then you're good. Yeah.
When you say it's hard to check whether there's a state corresponding to classical shadows, is it provably hard, or is it just we don't know how to do it yet?
So the 5-second intuition is, this classical shadow is this introduced by Robert Huang and Preskel, and I'm forgetting their Thank you. And it was this idea that, you take these, you represent the state by some Paulis that you've measured out, but the problem that you get is the representation is not necessarily a positive matrix. So it has trace 1 and is Hermitian, but you're not sure it's positive. And in general, I think when you generate the classical shadow, it doesn't generate a positive matrix. So it doesn't actually, it doesn't really represent a state by itself. You have to believe that it came honestly. Okay, so how does state NP play in here? Well, this idea is that we're here, it's conjectured to be QMA complete. So let's imagine that there's a state right there, which was in state NP. Okay, so that means you can describe everything about it. You can calculate the trace of O psi n for no matter what local observable. And what that morally means, right, is that you can actually calculate the energy of the state with respect to the local Hamiltonian. And you can calculate that exactly. So if such a state existed that was in state NP, then it would imply that QMA equals NP. So morally, if you believe this quantum PCP conjecture, it's actually saying something very strong about state complexity lower bounds. You could write this more generally. Yeah.
That last bit, sorry, what was this indicating?
Yeah. So imagine there was a state that had low energy below this epsilon threshold, and it was always describable in state NP. Then instead of providing the description of the quantum state, you provide just the description xn. And then a classical device can use xn to calculate the Hamiltonian's energy. And because it's in state NP, he's promised that a bona fide state exists.
Sorry, you need such a state for any Hamiltonian. Just for one Hamiltonian, one such state won't do the trick.
Yeah. So it's saying, yeah, it's surprisingly hard to disprove. Yeah, exactly. You want that for every Hamiltonian below this epsilon threshold, if there existed a state NP, then you have this contradiction. Okay.
I guess one could define a state QCMA, and the implication will also hold there. And
Right. So if you have a quantum PCP conjecture and you take any class below QCMA, you can pick whichever one's your favorite, it's going to imply some state C lower bound for the appropriate definition of state C for whatever that is. So what this does is this is a very simple way of extracting a minimum state complexity hardness from the underlying quantum PCP conjecture. You pull out everything about computation. You're just saying, I have to have these objects which have such state lower bounds. And in particular, when C equals NP, the quantum PCP conjecture implies state NP lower bounds for all types of state NP, but including any specific class of state NP. And the one that gave the community a lot of interest was this one that was called the NLTS, or no low energy trivial states conjecture, of their local Hamiltonian system, so that all the low energy states require at least a strong circuit depth lower bound. Okay, so this we were able to prove last year at about this time in June, and we showed that there's an explicit local Hamiltonian system so that every low energy state requires high circuit depth.
Sorry, I'm confused. I mean, couldn't you imagine a resolution of the quantum PCP conjecture that was just agnostic on the QMA versus QCMA question?
Yeah.
Yeah, okay. So then it wouldn't have to prove these state complexity lower bounds in that case, right?
Yeah.
Okay,
It's
all right,
you
fine.
require
Yeah,
this
fine, all right,
additional
understood. All right, okay.
expectation.
Okay, fine.
Yeah, so you could prove the quantum PCP lower bound
Yeah, fine.
and not disprove
Fine.
something strong.
Got it.
Okay, so this is based on a sequence of partial results, and it was saying something about how robust entanglement morally exists at low temperatures. But it was really based deeply on quantum error correction specifically high rate and high distance codes. And my goal for today is I want to say a little bit about why that was inherent and why that was the sort of the right way to prove the first example of NLTS, but maybe why it's the wrong way to prove the second example of NLTS. Why we need to do something a little bit different in order to, learn something a bit more. Okay. So, what should we try to solve next? There's two things which I think are somewhat reasonable. One is you can try to go and say, well, you set out this thing that there are stronger state complexity lower bounds. I need to prove state NP lower bounds for everything. I need to prove state MA or state QCMA lower bounds, right? Very reasonable things. I'll say a little bit about this. But what I think is actually interesting is to go some other way. And I want to think about how do we reintroduce computational hardness into the problem. So the NLTS was great because we extracted all the computational task out of it. It was just about creating a Hamiltonian with certain properties. But in the end of the day, if you want to prove the quantum PCP, you're going to somehow have to put that hardness back into the problem, right? So we need to somehow figure out a way to do this. So the two main suggestions I have is one is you could try to prove that quantum PCPs are MA hard. And there's a little tension there. There's this paper by Alex Grillo and Dorit about how a quantum PCP for MA, a roadblock that you have to avoid. You have to go around stochasticity somehow. But even before you try to prove that quantum PCPs are MA hard, I ask you, can you even prove they're BQP hard? Excuse me, BQP hard, or actually even BPP hard. Now, if you ask about BPP hardness, you have to make sure that you're talking about non-randomized reductions. But what I think I'd really like to talk to you about is there a way we can construct local Hamiltonians which simultaneously are all NLTS and they're NP hard? So it's hard to calculate the minimum eigenvalue, but simultaneously all the objects that we're going to ever consider all satisfy this NLTS property. And I'll say, I think, why this is, fruitful. But to do that, to come around to this question of simultaneous NLTS and NP, I need to go through a little bit about how we proved NLTS the first time. Okay, so what's the simple proof sketch? Well, you need a method for proving circuit depth lower bounds. NLTS is all about showing that the low energy states cannot be generated by short circuits. So somehow, somewhere in there, you have circuit depth lower bounds. Okay, so here's the simple fact that's very useful to know, which is that for every depth T circuit, there is a local Hamiltonian, which is 2 to the T local, and has a unique ground state of C applied to that state. And the spectral gap is 1. It's a very simple Hamiltonian. You just take the Hamiltonian, which just checks that your state, is all zeros, and applies C on it. Okay. And you can prove this one very easily. The only hard part that you need to do is prove the 2 to the T locality, right? The spectral gap and the unique ground state just occur because you rotated a known Hamiltonian by a unitary. But the depth may be not intuitive, but you do this by induction. So initially, you have it, and then as you apply a layer of gates, you show that the locality only goes multiplicatively by size 2. Okay, so when you think about low depth states, you should always be thinking about this Hamiltonian, which captures that state. Okay, so then you need a second result. And the second one is this sort of interesting point that, let's say you have a set of points x1 through xm. Okay, they're in the Boolean hypercube. And you have the property that the distance between any 2 points is at least L for some constant L. Then any state which is supported on x1 through xm, any state, that it cannot be the unique ground state of an L local Hamiltonian. Okay, this is the second big idea. It's very simple to prove. So here's the idea is, okay, psi was this way with this coefficients alpha j. Let me just take x1, the first one, and let me flip the coefficient on x1. Okay? And now let me compute the energy. So to compute the energy of psi with respect to any Hamiltonian, I just need to add up all the energies of the local terms, right? Think about any L local term h. And what you're going to get is that this first line is just the expansion of the computation, nothing fancy. But the second line, I have forced j to equal j prime. And the reason that is precisely because of the assumption I have the two xi and xj, they differ by L. So because they differ by L, the only terms of these that are non-zero in this summation have to be those that j equals j prime. So you get to remove it. And now you get that alpha j squared, right? And now you can say that that has to be the same energy as psi prime. Because notice that, if the same thing would have occurred, except that minus sign, you would have gotten two minus signs inside this absolute, so nothing occurs. So what it really says is something even stronger, which is that if you had a state which was of energy, something, with respect to such a Hamiltonian, if you added phases, nothing would change. The energy would stay the same.
Do you want a plus sign on the top in the definition of psi prime?
Absolutely.
Not,
Yeah.
Thank
There's a
you.
plus. Sorry.
Thank you.
So you put that corollary back with we combine these two facts, right? One, that if you are a low-depth state, you are the unique ground state of a local Hamiltonian. You combine this directly, and you get that any state which has such a property is not the output of a low-depth circuit. There's a picture you should think about, which is that you have a set of points, where the distance between them is all L apart. But I'll claim that it's not much harder to show the following extension, which is instead of just specific points, x1 through xm, I think about some subsets of points s1 through sm, where I have again that the pairwise distance between these sets is something large. And then it says that if you have a state which is again supported on these sets, so that the vector Vj is just restricted to the jth set, then this is not the output of a log depth circuit either. And this is some distribution which we call in our paper a well-spread distribution. And in fact, it's a nice starting result, which says that any state which is exactly supported on these subsets cannot be the output of a short circuit, but it's not a robust result. But I claim that it's actually not that much harder to even make it robust. You can make it to this very simple setting where you have two sets, S1, S2 even, and the distance between them is L. And as long as they put mu mass on either of them, you get a circuit lower bound of the following form. So L, as long as the larger L is, the stronger the lower bound. The more mass, the stronger the lower bound. But there's this pesky 1 over n term. And that's actually coming from robustification due to Chebyshev polynomials that we don't know exactly how to remove. Okay, but at least I should convince you that this is a good technique for proving lower bounds, is finding well-spread distributions. Well, it seems like a good way of doing it. And the reason why these lower bounds exist is they're completely information theoretic. It's just about how fast can information be propagated. It's not saying anything much more complicated than that. But the unfortunate problem is that this is really the only way we know how to prove lower bounds for quantum states, explicit ones. There's specific other examples and counting arguments that get you other lower bounds, but if you want it explicit, this is morally the only really robust technique. And you need a robust technique because we have to prove lower bounds for all low energy states. So whatever lower bound technique, it should be amenable to small perturbations, right?
Perturbations on the state.
On the state. And in the energy space, actually. But okay, so how do you find a well-spread distribution? Well, there's one natural one that's always hiding around whenever you think about error correction, even classical error correction. Because you think about classical error correction, in my mind, it always just looks like a set of points whose distance is far if the code is good, right? The distance between any 2 points. And this is a very good way of viewing the exact solutions. But you could ask, what does the low energy state look like? What happens when you say, I don't necessarily just want to satisfy my linear equations, but I want to satisfy 99% of my linear equations? Then what you get is that if the matrix that describes the code, really corresponds to some small set expander, you get the following. Well, first of all, you're going to get these kind of bubbling out around each of the code words, because any of those things will be a small perturbation of the code, so it's only going to change on the checks that detect that area. But the second thing that's sort of interesting is you get these additional sort of bubbles that occur far away. But the property being that if you're small set expanding, you get that the distance between any of these bubbles, any of these regions, still scales with the distance of the code. And so you get sort of this picture that, it looks exactly well spread, right? It's got everything we need. So we say, okay, well, this seems great. We're going to prove lower bounds because we have well spread distributions and they arise very naturally from codes. And that seems to be our only technique for proving lower bounds. But here's the problem, which is that if there exists a low energy state psi, which is supported only on these purple regions, or you could go to like it has most of its support on them. But then what you get is there has to exist a state phi with the exact same energy, but that is only supported on exactly one of those purple regions. And the argument is exactly the same as we did before. I have the same argument written down one more time, except now all I ask you to realize is that the linear combination of psi and psi prime, where I added that phase, right, is just going to be the vector Vj. Right? Sorry, this should be psi minus psi prime, excuse me. But if you take psi minus psi prime, the only terms that will remain are the terms in the V1 direction, right? So since 1 was arbitrary, you can prove this for any of the regions. So you hit this sort of annoying but inherent predicament, which is that if you find a state psi that's well spread, and then you even happen to go around and you find a local Hamiltonian which had psi as a ground state, then you inherently will always find these states phi, which are only supported on one region, but they're also ground states, right? And the same would occur with low energy. But then what do you get? You have the problem is how do you prove that phi is well spread? Because the whole well spreadness was in this specific basis, and you saw, but now it's incredibly clustered. So what are you going to do? Okay, so the saving grace is that there's sort of two measurements you could take. So if you have a state psi, we were talking about what the z measurement distribution looked like, but we could also talk about the x measurement distribution looked like, right? And the simple idea is that whenever the state's measurement in one basis is rather certain, then the measurement in the opposite basis is rather uncertain, right? So if you're very concentrated in one picture, then you're very unconcentrated in the other picture. And you can formalize this by some very simple calculations. You can put this as like a homework problem in like first quantum computing class to show that whatever mass, if you put a lot of mass on S in the Z picture, then consequently on the small t's, you can't be putting very much mass. But still, this doesn't answer anything because all this says is that if I'm highly concentrated, like the state phi would be in the Z picture, I need to show that the X picture of the same state is disjoint, right? That it could look like one contiguous blob, but I need to show that in the X picture it's well spread. And that doesn't seem immediately clear. But to provide some intuition for you, here we should look at the toric code. So in the toric code, when you measure in either basis, you get this idea where you get that there are 4 regions, and they correspond to 4 different types of measurements. So the first type of measurement corresponds to trivial loops, right? If you measure, you'll get out some trivial loop. Another set corresponds to any loop, anything which is topologically equivalent to one of the logical loops. And then the other 2 are just, the other loop plus the linear combination of the other 2 loops. You get these 4 different regions, and it's not hard to argue that the distance between these regions, between non-trivial loops and any of these, is scales like square root n. And what you get is actually, I claim that you'll see exactly what I was telling you the last time, which is that these loops actually correspond to 4 different states, right? If you think about the toric code and we think about the standard x and z operators that we write down in the toric code, the set of, if you had the state that was logical 0, 0, the only measurements you'd get are of this type. Logical 0, 1, you'd only get measurements of this type, etc. right? But that's in one of the two pictures. But when you take the other picture, right? If you look at the Hadamard picture, then 0, 0, its Hadamard transform is plus plus. So if you're completely concentrated on diagrams of this type in one of the pictures, you're extremely well spread on all the diagrams of this set. So the sort of the symphony that occurs in quantum error correction is sort of the right picture to get this well spreadness in both of them. So what we want is we want to do this exact same thing. We want to show that low energy states, when they're measured in the z basis or the x basis, they're well spread. The key word is or. We can't hope to get well spreadness in both bases. Okay? And here's where something that had bothered me a long time, and when I gave this talk on the virtual seminar, Matt Hastings asked, why is high rate necessary? Why was the rate a big part of it? The reason the rate was there was it helps prove that these bubbles are small. The higher the rate, the smaller the size of the bubble, which means that when it's concentrated, the more it's concentrated in one basis, the less it's concentrated in the other. And that playoff was really necessary. Distance was needed because you needed to prove robust, well-spread lower bounds. You needed to prove that these kind of things spread out. And the expansion was needed to show that when you look at the low energy solutions, if they don't fall in a specific cluster, they move to another cluster, but the clusters are well designed. It's an open question of whether this expansion is explicitly necessary, whether you need to explicitly assume it. In the classical case, you can prove that whenever your code has high rate and high distance, it is necessarily expanding, but we have yet to be able to complete that argument in the quantum setting.
Sorry, what does expansion mean? Just that the constraint graph defining the code as an expander graph?
Yeah, exactly. The code itself, the CX and CZ codes themselves will not be good expanders, right? Because like the toric code is an example. They're terrible codes, right?
Right.
But like the modulo, the CX mod CZ, that there's a notion of expansion that has to be in there.
Okay.
There was actually a very nice talk 3 weeks ago in the Boolean hypercube program by Hopkins about this object and why he really thinks it should be called small set expansion. Yeah. Just that like it clusters well.
Oh.
Okay. So let me get back to what I wanted to say, which is let's talk about how to create local Hamiltonians which might simultaneously be NLTS and NP. Yeah.
Here, somehow you're saying, okay, error correction codes are fundamental for NLTS. Would it be possible, or if it doesn't make sense to think the other way around, like an NLTS Hamiltonians could be used to design code?
Yeah.
Is it, okay.
I don't think there's any explicit argument there, but it might be possible. Yeah. I don't think they're like inherently tied. My hope is that there's ways to do NLTS which looks a little away from codes.
Okay.
And I'll try to motivate that. So our construction was a stabilizer Hamiltonian, but stabilizer Hamiltonians, they're not very computationally interesting because when all the terms commute, you actually know the minimum eigenvalue. It's always going to be 0. And in general, they're easy to analyze. So the question is, can we construct some Hamiltonians so that it is NLTS? That's requirement 1. And the second requirement is that it's going to be hard to decide the minimum eigenvalue, at least NP hard. So here was the first idea, which is you could say, well, let me just sort of encode my NP problem. So let me try to think of my favorite NP problem. It's some CSP, C. I'm going to construct a Hamiltonian whose ground state looks like this. It's just this uniform superposition over solutions. But then it looks exactly like the same picture we had before, which means that unless the Hamiltonian was highly local, where L is the distance between the solutions, then every X is a ground state of this Hamiltonian. And morally, what you're getting back to is that your Hamiltonian is just the classical Hamiltonian for the CSP, since it's accepting every solution all by itself. Right? So you weren't able to add this quantumness directly. So this doesn't work. There was a very nice proposal that came from 2 results. One was by Anurag, Anshu, and Nico, which was the precursor to our NLTS result. And the other one was by Anshu, Gamarnik, and Bobak. I forget what Bobak's surname is. Kiani. Okay. And it says that, well, let's take a yes CSP and let's explicitly route down a Hamiltonian whose ground state no longer is just supported on those solutions. It's now supported everywhere, but there's a decay. And the decay is proportional to how unsatisfiable that string is. So for every string X, based on how unsatisfiable it is, there's a delta decay. And for delta being, constant, you can get a Hamiltonian whose spectrum with each local term is bounded. So really what you get is you get this following picture where you sort of have this probability distribution that peaks at the points, but then sort of decays out, right? And then what you get, though, is that this Hamiltonian, if you measure this Hamiltonian, you're never going to actually get a solution X. Those occur with very small probability. But what you'll get with a decent probability is you'll get something which is close to a solution. So if you, instead of thought of your constraint as just a classical thing, but it had some sort of PCP-ness to it, I'm speaking very broadly here, then you could maybe get the solution and correct back. So you now have somehow encoded the NP-ness into the problem, and you have a sort of an interesting quantum state. You can write down this explicit Hamiltonian, but we don't need to talk about it explicitly. The only problem is that while this Hamiltonian is what's called combinatorial NLTS, which is a softer requirement than specific NLTS, it doesn't look like it's NLTS. That's because we can't seem to prove lower bounds for it. And that's because morally, when the solutions to C correspond to what's called a collapsing hash function, there exists a non-well-spread energy state. And a collapsing hash function, it's a cryptographic notion, but roughly speaking, what it means is it's BQP hard to distinguish the uniform superposition over solutions from any single solution. So what you get is that if there was a low energy, if the ground state looked like this, then there was a low energy state, which was just that you took the ground state and you pruned it to this orange circle around it, and that was very low energy, which means that the checks in the bulk, like the bulk of the area between the peaks, don't have much weight. Yeah.
But collapsing hash functions are most hash functions, presumably, right? Yeah.
Okay. So, but the real issue is that this Hamiltonian, we defined it too much in one basis. It was too Z basis dependent, right? It was saying, I want this problem as one basis. So the question is, can we do something a little bit different? And I got excited this, and I thought it's worth mentioning this, what I think is a surprising connection to quantum money or lightning, which is in the quantum money proposal by Zandri, he had this idea that, okay, there's a hash function, and there's this thing called the money state, and it's proportional to the set of solutions. Okay, and he has this beautiful theorem that says, hey, if H, the hash function, is collision resistant, which means given a solution, Hx equals S, it's hard to find another solution, and non-collapsing, then this is a quantum lightning scheme. I don't know how to say much about this, but I can say the following thing, is there's sort of two issues. One is if the solutions of H inverse of S, their distance from each other is at most L, well, then there is an n to the L time algorithm for finding the next solution, right? So it says that at least the solutions have to be somewhat far apart in order to have the collision resistance. But then the H is collapsing, and any algorithm that looks like Hamiltonian energy estimation for an L local Hamiltonian seems hard. And so it proves one thing about quantum money, which just says that, look, if you're going to have this, your algorithm has to be very far from a notion of Hamiltonian energy estimation. It can't look like this. Right? So there's an intermediate problem, which I think is worth thinking about for both Lightning and PCP, which is to take NP problems C1, C2, they could be equal, it doesn't matter. And you want to construct a Hamiltonian whose ground states has sort of the following measuring statistics, which is that in one picture, you can, given a measurement in that purple region, you can derive a solution X so that it's a solution to the first to the first CSP. And in each of the bubbles, you derive a different solution. And the same thing for the second thing. But there's a key desired property you need, which is that if you measure a ground state, it gives you some entropy over solutions to either C1 or C2. So either you can, right? And this is just because of the duality, that you can't be too certain in one picture and the other. Right? And you should be thinking that this picture should morally really represent you sort of like the codes. So in some sense, what we're looking for is something that looks kind of like coding theory, but is encoding NP problems. So we're sort of trying to look for hypergraph products of NP problems. We know how to take hypergraph problems of like equations like AX equals 0, right? That's how we form these quantum codes. But I'm asking for something much stronger, which is, can I take the hypergraph product of NP problems? Anand?
Is it clear you can do this even without the key desired property, like two CSPs?
No, I don't think so.
So even that's not.
Even that. This is, I think, a very exciting avenue to explore. Okay, if anyone has a name, that would be also helpful.
How is this different from encoding a record encode of the witness? Because you're assuming that you're imposing that the C1 of X is 0?
Well, so with the error correct encode, you do get this, but the CSPs you get just correspond to codes, so they're trivial. They're like just linear equations of the type, AX equals 0. Right? So there's not encoding any computational hardness. If you encode equations which are like AX does not equal 0, then like Hastad's PCP even gives you like maximizing problems over those are hard. Or if you included quadratic equations, right, you can get hardness that way. But taking the hypergraph product of equations that are not just simple kernels, or taking hypergraph products of quadratic equations, I'm not sure what the right notion is, even on whether it's a vacuous object or not. Okay, yeah, so please, if anyone has ideas for names. Okay, the next thing I think we could try is maybe we go back. Maybe we step back and say, let's think about stronger state complexity bounds. And there's a set of objects which I think are very interesting, which I call trivially rotated stabilizer states, which is a very simple idea, which is you take a Clifford circuit and then you allow yourself to run a constant ebb circuit on top. These also form a class of state NP witnesses, but they seem rather strong in the sense that any state of this type, it doesn't satisfy, our previous proof of NLTS, can be broken by such states. Right? Because the Clifford gives you all the strength. Because the Hamiltonian we have in NLTS is stabilizer, so its ground states are Clifford states. So this gives you all the strength you need. So thinking about this conjecture might force a new method of proving lower bounds for quantum states, which then resets the whole clock, right? Because then we get to start from the beginning and we don't hit these kind of apparent contradictions. The other thing is there were, I should mention there were some really nice conjectures, one called the NLTS by Garabian and Legal, and then, this proof that there is a state that's simultaneously not stabilizer and no low energy sampleable states, I think. But it really was sort of asking for a specific state MA lower bound. And that's something that's worth, trying. Or I think, you go back and say something about how quantum PCPs are, try to provably show MA hardness, BQP hardness, BPP hardness, try them, but there are natural barriers in that direction.
I mean, in one definition, at least, of one PCP, it is trivially BQP hard.
I mean, not that definition. If it's trivial, it's not the other definition.
What's the definition, actually?
I mean, the definition of gap amplification versus the definition of probabilistic accessibility to the truth. And the probabilistic accessibility to the truth, then it's trivial because then you have a BQP circuit that accesses the truth.
Exactly.
But they are quantum. I mean, by quantum reductions, they're equivalent.
Like every quantum reduction is showing BQP hardness is not good.
Exactly. So right. So that's why these even showing BPP hardness, right? You have to choose the right reduction for the problem to be interesting. Okay. Last thing I'll say is that you might say, okay, well, the classical PCP theorem was inherently based on error correction. So maybe I need to just apply quantum error correction to a ground state of a Hamiltonian and sort of massage my way up, right? But there's a problem with quantum error correction codes, which is a very simple folklore theorem of local indistinguishability, which says that the small reduced density matrices of codes are invariants of the encoded state, where d is the distance of the code. It's a very simple proof, and it also plugs that no cloning theorem issue right in the heart of it. So no cloning, right, just says that this sort of transformation is nonlinear. Quantum error correction would say, well, okay, if you have an error, let's say these red qubits, if it's a correctable erasure error, then what that means is that you could remove those qubits out, and then given the state remaining with the hole, you could regenerate those qubits. But now you have two copies of that, the state that was there. So the only reconciliation of this that you've apparently done some quantum cloning, is that the reduced density matrix on that small region was completely determined by the code. It doesn't actually contain any information. You could have just generated that reduced density matrix state for free by yourself, right? So it tells you that there's no information in these local regions. So why does that have an issue? Well, I'm paraphrasing and trying to be as general as possible. Like if you're in the elevator and you have to explain to someone the PCP theorem, you would say that it's, you apply an elegant, locally testable code around a satisfying assignment of formula. That would be, like a 5-second description. But you can't do the same thing for quantum PCPs, because if you used a code with distance d, then in order for the local Hamiltonian to be able to distinguish yes and no instances, it has to have a locality bigger than d. But if we're looking for constant locality Hamiltonians, then you were using a very, very weak code in the first place. So why did you use the code at all, right? Did you gain anything from using it? Probably not. Yeah, and I think that's the last thing I'm going to say. So.
What happens if you think about a not so local Hamiltonian?
You mean, can you prove? So for one, if you think of a non-local Hamiltonian, non-constant locality Hamiltonian, NLTS is trivial. But it's even open, I think, if log local Hamiltonians, you can prove the quantum PCP conjecture. We tried at one point, remember, with perturbation gadgets, unsuccessfully, to even get log local. But yeah. Any other questions?
This is a bit about local decodability, like this question.
It just says that, like, if everything was wrapped in a code, like you knew the solution was a code state, then there was no real information hiding in the small measurements, right? So the idea is that if there is a quantum PCP conjecture, that the reduced density matrices themselves, even though they're small, they carry a lot of information, right? Principally, it tells you that, if there was a quantum PCP conjecture, the local reduced density matrices do not look like maximally mixed states, right? Because if they all look like maximally mixed states, then the maximally mixed state is a solution, right? So that tells you that some of the reduced density matrices have to be far from maximally mixed. And codes, for example, the reduced density matrices are basically maximally mixed.
You mentioned that there are some examples of circuit that go on some quantum states that don't look like quantum. You said there was like some very specific examples. I've never seen an example that doesn't allow this.
Yeah. So one example that Natalie and I worked out earlier this week is, if you wanted to prove that there was a phase state that was far from Clifford's. So the Clifford states really look like phase states with quadratic phases. Phases are defined by quadratic functions. So if you take a higher degree polynomial, not too high, like a degree 5 or something polynomial, you can show it's very far from all of these Clifford states, right? So you can come up with lower bounds in that technique, and that seems very different.
Chemical polynomial there, we have trouble with.
question was about the Chebyshev polynomial for robustness. If there's a gamma function, we have.